Okay, ladies and gentlemen, thank you so much for that introduction. This is a recording, so I didn't actually hear it, but I'm sure that it was great. Now, my article is called Simulated Effects of Wet-etched Induced Surface Roughness on Infrared Transmission and Reflection. And it is written by me, Phillip Papatzacos, and my supervisors, Mohammed Nadim Akram, Eivind Bardal, and Per Ølkers. Now, as we know, a thermal image sensor has been developed, but it requires vacuum to operate.
So our idea was to take a silicon wafer, etch a cavity into it, and then hermetically seal it over our sensor. Unfortunately, etching silicon in real life, unlike in PowerPoint, does not leave a completely flat surface. And since we're going to send an image through this cap, we want to investigate what this surface roughness does to the incoming light. So we took a wet-etched piece of silicon and scanned it with our trusty AFM and exported the data into COMSOL multiphysics. Now this allowed us to create a model where we could send infrared light through our surface, but also manipulate the surface.
So we've made a simulation where the measured lines define the transition between silicon and vacuum. We've placed absorbing layers on top and on bottom, and made a transparent import, and defined lines where we measure how much light passes through the surface and how much is reflected. Now, since one side of the silicon will be polished and therefore almost perfectly flat, we've chosen to only simulate the silicon vacuum transition. Now, we do this by taking 10 random lines from our AFM scan, and for each line we increase the roughness by multiplying the y deviation by an increasing integer, and investigate what happened to transmission and reflection as we changed the angle of incidence and as we changed the wavelength from 8 to 12 micrometer. After all the simulations have been completed, we average our results and end up with these two plots. The first thing to notice when we look at the figure 4 on the left is that for the wavelength sweep with increasing roughness, the results are actually fairly stable, with the transmission coefficient only ranging from 0.66 to 0.8. A clear trend we can observe, however, is that there is a clear increase from 0.7 to 0.78 plus minus 0.02 at RMS surface roughness of approximately 500 nanometers, meaning that wet-etched induced surface roughness in this range might actually help transmission, not prevent it. This peak in transmission can actually also be observed in the angle of incidence sweep, figure 5 on the right here, if we look at 500 nanometers at 0 degrees incidence angle. Now, continuing to look at figure 5, which is the angle of incidence sweep, we see that as the angle of incidence increases, the transmission coefficient drops to 0 at approximately 20 degrees, which corresponds to total internal reflection. We can also see that between 20 degrees and 40 degrees, an increase in RMS surface roughness actually increases our transmission coefficient. This makes intuitive sense, considering that the increasingly sharp peaks will be more normal to incoming light at increasing incidence angles, which again aids transmission. It is, however, worth mentioning that the higher the surface roughness, the less similar our transition is to the original measured surface, which is likely to make our simulation less valid. Simulation results can be interesting, but are generally useless if they don't relate to the real world. So an often used technique for validation is comparison to an analytical estimation. So we compared a completely smooth transition to the theoretical reflectance given by the Fresnel equation. These results are seen in figure 6, and we see a near perfect overlap between our simulated results and the analytical results. This is, of course, only for a smooth surface, but analytical results for this exact type of surface is actually not available. Another indicator of simulation validity is to add up the simulated reflection, transmission, and absorption coefficient. And in a valid simulations, these fractions should theoretically add up to unity. Now, in figures 7 and 8, we see that our simulation actually does this fairly well, especially at lower roughnesses and angles. So to briefly conclude, for light wave infrared light with wavelength 8 to 12 micrometer, wet-etched induced surface roughness is not a concern when it comes to reflection and transmission. This hasn't been directly mentioned, but it can be seen from the figure as the difference between a flat surface and one with roughness is negligible. We have also seen that for angles between 20 degrees and 40 degrees, higher surface roughness may actually lead to lower reflection and higher transmission. Now, our most interesting result is that for wavelengths between 8 and 12 micrometers, wet-etched induced surface roughness of up to 500 nanometers may actually lead to lower reflection and higher transmission. Now this roughness is still less than 1/10 of the minimum wavelength, which means it is unlikely to distort the image. This again means that for our device, instead of worrying about the surface roughness as a result of etching the cavity, we could actually alter parameters to increase this roughness, and as a result get more of the incoming light to our image sensor. With that, I conclude my presentation of my article, Simulated Effects of Wet-etched Induced Surface Roughness on Infrared Transmission and Reflection. Mention that the full article is available through IEEE Explorer, and thank you so much for your attention. Goodbye.